Welcome to the first lesson of Math 3. In this module we will discuss graph theory, and all of the subjects are given with the help of videos. You will also find videos of the extra assignments, and some of the videos are made by me, Ella van der Sande, but most of the videos are made by a colleague of mine, Mrs. Louisa Papa Christodoulou. I hope you enjoy this Math 3 module. Information is there in the book Discrete Mathematics, which we will also use for Math 1 and Math 2, and there's an extra reader for some extra explanation. You can find the course description on the general channel in Teams, and you can find specific exercises and all videos and the extra reader on the Math 3 lecture channel. Course planning is quite straightforward, so we have 3 weeks and where you have time to do the lessons 1 until and including 6, do all the exercises, and every week you will have plenty of time to, via Teams, contact me and ask questions about assignments you didn't really grasp or some theory background. And in week 4 we will have a written exam at Fontys University. There's a special thing in this written exam. You are allowed to bring from home one double-sided A4 with your own personal notes. You can really scribble them very small, or you can type them, whatever you like to do. And this is because Math 3 consists of a lot of definitions, and we really don't want you to learn all these definitions by heart. So just put down the definitions you think I will forget at the exam on this double-sided A4 paper. In this first lesson we will look at the book in chapter 8, and by the way, in the reader every time before we start some extra explanation you will find exactly what parts of the book are discussed, and also you will find this in your description book of the complete modules. So in this lesson we're going to give you an introduction about graphs and multigraphs, and in the next video we'll continue with paths. Well, you have several types of graphs, like this temperature graph from New York City, or something in a column line description, but the graphs we will discuss are these types of graphs. And so graphs which have vertices, which are the dots, and edges, which are the connections between the dots. And if we have a graph, we denote it in a mathematical way with a name. So in this case we've called the graph G, and it has 2 elements. It consists of a number of vertices, the black dots we saw in the previous slide, and a number of edges, so the connections between them. And you can all have all sorts of connections. So if we specify a little bit further, we can talk about a graph G, which has 4 dots, 4 vertices, so A, B, C, D, and 5 edges. Of course I can't tell what the edges are, so I need to specify the edges, and we do that one by giving a begin point. So E1 is an edge from one node, for instance A to C. So then E1 would be this edge. So if we look at a complete example, that could be something like this. Then A is connected to C with the edge E1. So E1 in this example would be AC. E2 would be AB, etc. So we just have a collection of vertices, of nodes, and a collection of edges, the connections between the nodes. So vertex, edges. Why do we use graphs? Well, you can imagine in computer theory we use it to optimize networks, but in history it was also used to optimize railroad networks or find a shortest or fastest path, like in a TomTom from city A to city B. So it has all sorts of useful possibilities. For instance, if we look at this network between cities, then you can represent this one as a graph, and you could say, okay, all the edges are, for instance, direct line flights from London to Paris and from Paris to Brussels, but we cannot fly directly from London to Amsterdam because there is no edge there. So it can represent all sorts of things. Okay, let's look at a specific graph. It has vertices u, v, w, and it has edges uv, this one, vw, this one, and wu, this one. This graph is said to have vertices u and v who are adjacent or neighbors. So what does it mean? If we have an edge from u to v or vice versa, then these two vertices are adjacent, are connected together. You could also say we have an edge, like this one, let's call this E1. E1 is incident to u because one of the endpoints of E1, or the starting point of E1, is this vertex. So in this graph we could say that E1 is incident with u, but it's also incident with a v. So an edge has always two vertices to which it's incident of. And by the way, it could be the same vertices. So I could make an edge like this from u to u, then E1 is incident to u twice. If these edges are duplicates of each other, so if there are two ways to go from u to v, to edge E1 and to edge E2, then we call it a multigraph. So if there are more edges to go from one vertex to another, then it's a multigraph. We can also look at a loop with two endpoints. And a definition of a multigraph is a graph which has multiple edges or loops. So this graph is not a multigraph, but as soon as I put in a loop, it becomes a multiple graph. So either it has two edges with the same beginning and the same end, and it has a loop. And then we call it a multigraph. Another definition we can look at is the definition of the degree of a vertex. And the degree of the vertex is just the number of edges which are incident with that vertex. So for instance, the degree of u is 2, because it has two edges, this one and that one. The degree of v is 3. The degree of z, that's a special one, is 0. And this one is also called an isolated point. And then take note, if we have a loop, so let's say we put a loop here in w, then the degree of w is not 3, but it's immediately 4, because the loop has a starting and an end point in w, so it has this edge, and twice the loop. So the degree of w is 4. A very nice theorem is that the sum of the degrees of all the vertices is twice the number of edges. And the explanation is very simple. If we have a vertex, let's say we have this vertex u, then it's connected to v with this edge. Let's call it E1. So E1 is connected to u, but an edge always has 2 points it connects. So in this one it goes from u to v. So this same edge is counted in the degree number of v. So every edge from a graph is counted twice. So the degrees of all vertices together is twice the total number of edges. And that is with an expensive word called the theorem, theorem 8.1. So let's try to read it. The sum of all degrees of vertex or vertices in a specific graph is 2 times, and this sign is the number of, is 2 times the number of edges, so 2 times the number in the set E, the set of edges. And in this example, let's check it. The graph G has 4 edges, E1, E2, E3, E4, so that's 4. So E equals 4, and the degree of U is 2, the degree of V is 3, X is 1, W is 2, so the sum would be 2 plus 3 plus 2 plus 1 is 8. So indeed, the sum of all the degrees is twice the amount of edges. It will be a very useful theorem in later exercises. So let's try to do that one in an intermediate exercise. So we have a graph named G, and we have 10 nodes, and we have 18 vertices. And then it says it has 2 vertices. So apparently we have 2 vertices with degree 3, we have 3 vertices with degree 2, 1 vertex with degree 4, and n vertices with degree A. And if we add all of those up, that would be the total degrees we have. That's the sum of all the degrees. So if we do that, that would be 6 plus 6 is 12, is 16. So 16 plus n times A, that would be twice the number of edges. So that would be twice 2 times 18 would be 36. We also know the number of vertices, and that would be 2 plus 3 plus 1 plus n. So that would be 6 plus n, that's the number of vertices, and that would be 10. So now we have 2 very simple equations, and we can solve them. So 6 plus n equals 10, that means that n equals 4, and 16 plus 4 times A equals 36, so 4 times A becomes 20, so A becomes 5. And so we have n vertices, 4 vertices with degree 5. Another question would be, is it possible to have a graph with 5 vertices, where all these vertices have degree 3? So the sum of all the degrees in this graph would be 5 times 3, which is 15. Well, okay, you can already tell that if we would divide that by 2, because 15 would be 2 the number of edges, then the edges would mean we have 7.5 edges, which is apparently not possible. So the answer would be no, that is not possible. Last definition we'll talk about in this video is the definition of a subgraph, and that's quite straightforward. So a subgraph of a graph G in this example is just a graph which has part of the vertices of the original graph and part of the edges. So for example, if we look at this graph H, U, V, W, X are all elements of the original graph, and also the edges, so this one, and that one are also there in the original graph. So, and then we talk about a subgraph. In this example, it's not a subgraph, because look, we have this edge WX, which is not part of the original graph. So then it's not a subgraph. So all elements of the subgraphs should also be there already in the original graph. Okay, that concludes this video. In the next video, and that will be given by Mrs. Louisa, she will talk about paths in graphs. Hope you enjoyed this first lesson and see you at the Teams meetings.